Okay, so from yesterday, we were talking about the idea of finding volume. I wanted to show you this picture that somebody had. Let's see here. This might help you see it a little bit better. I don't know. We'll see.
Class makes me scared of learning.
Okay, so there you go. Take a look at this. Okay. This might help you understand what's happening here. You have a function that says y equals x squared here. So on the xy graph, you have y equals x squared. And then from that, you have different shapes that are coming out of the graph, three-dimensionally. Okay? And so since some other calculus class did this project, we get to glean from it the benefits of that class without actually doing the project. See how that works?
But I want to do a
Okay. So in the upper one, this might help you understand the idea of what we were doing yesterday. In this, what are the cross-section shapes? They're squares. And so what they did was they cut out a bunch of squares. How did they know to cut the squares to a certain size? They would figure out the distance from the x-axis to the curve, and that would be the base of the square, right? And then the height would be the same value. And so they cut a bunch of squares that had different sizes, and obviously as the function increased, the squares got bigger. Here they have triangles, right? And so same thing. They had to figure out the length of those bases. Here we have semicircles, right? And then here we have rectangles. Let's take a look at this one real fast. Let's do this problem. You have y equals x squared, and we want cross sections that are perpendicular to the x-axis are semicircles. Okay. I want to know the volume. Of the region, I guess, of the solid. Bounded. What would this say? Bounded by what? Well, by y equals x squared, the x-axis, and let's say x equals 4. Okay? Well, we'll walk through this, make sure you're good. What is the general form for finding volume? From yesterday, what did we talk about? Right. It's the integral. It's the integral of the area function times dx. And so trying to understand what this is, the area is represented by what? It depends on the shape, right? So in our case, what shapes do we have? Semicircles. So basically what we're doing is we're finding the area of a semicircle, and doing what with it? Multiplying it by a really thin slice. You know what I'm saying here? This thin slice is what? Dx. Okay? I drew this a little bit off, but in these semicircles, the thickness of the cylinder, as it were, or the prism, if you want to call it that, is dx. So what is the area of a semicircle? 1/2 pi r squared, right? You guys okay with that? Okay. Now I need to get this area function in respect to x so I can plug it in here. So what is it I need to know in order to know the area? I need to know what r is. Well, looking at those circles, what would represent the r, maybe? Any ideas? We're cutting it this way. So what was that? Half of y. Why? Because if I was cutting these circles out, these semicircles, what is the distance from here to here called? That's your diameter. Well, what it represents the diameter? It's your x squared function, right? So remember, on the x squared graph, this distance is what, essentially? It's whatever f of x is, right? That whatever value this is how high it is. But when we're talking about cutting and making semicircles out of that, that represents the diameter. So let me write that down. Let's say the diameter is what then? X squared, according to ours, right? So then what would the radius be? I'm going to say 1/2 x squared. Try and avoid the x squared divided by 2, only because analytically it's going to get messy if it's that way. So now what do I do with this? So you get area equals 1/2 pi times 1/2 x squared squared.
Most of this is just like recognizing kind of manipulating variables.
No, most of it's recognizing how to find the area of the shape. Honestly. Manipulating, what do you mean manipulating variables?
Finding R and I.
Yeah, I mean, yeah. Yeah, sure, okay. So what do I do with this? So this is the area function now. It's in respect to x. What do I do with it now? Plug it in, right? So it's the integral of, you want me to make that prettier? Okay. What do we get? I don't want to make it prettier. Well, because I want you to see it in its basic sense. So 1/2 x squared squared. That's your area. And then dx, what's our limits? 0 to 4. You guys okay with that? Okay. Now you can simplify it and use your calculator and evaluate and all that. But that's the setup. It's always the integral of the area function. The area is your integrand, and then you have dx. If we were cutting it the other way, then it would be dy, and we will explore that later. Wasn't that bad?
It doesn't seem so bad because I wasn't doing yesterday.
Okay. Fair enough. Maybe I just made it a lot easier for everybody. Did that help at all or no?
Yeah.
Okay, a little bit. Here's the fun stuff, the disk method. The disk method.
The what?
We are going to do basically the same thing, but we're going to be talking about disks. If you think the picture that we were talking about, what did the person do? They cut out a bunch of shapes. They cut out a bunch of semicircles. They cut out a bunch of rectangles or triangles that were all different sizes, right? Well, and then they basically glued them right next to each other. You know what I'm saying? So to find the volume of the whole thing, they found the area, in a sense, the volume of each little slice. So when I say the disk method, what shape is that? A circle, but what three-dimensional object are we talking about? Cylinders. So it's like taking a quarter or a pancake, different sized pancakes, and putting them next to each other, and then finding the volume of the object. No, hash browns are not circles.
No, hash browns, yes they are.
I
make hash browns.
Before they're the potato is a lips.
All right.
What is that called? Like the shape of a potato. It's not a sphere.
If somebody were to show you the shape of a potato, they'd say, what shape does this look like? They'd say, a potato.
Okay, I know it's an oval, but like, what's the name of
An ellipse, maybe? I don't know.
Okay.
Actually, that's what we're talking about today.
Potato.
The shape of a potato. Okay. Shh. Oh, I forgot. Jenny loves potatoes. Okay. All right. So the disk method, we're going to get to something else called the washer method in a little bit. Gail's going to be talking about the shell method in a little while if he hasn't already. Okay? All right. So what the disk method does, basically what we're going to do is take our, hopefully, geometric knowledge. Let's see if I can do this. If I take, let's say this is an axis, okay? This is an axis. And I have some shape over here, some function, something, some curve over here. And I revolve that curve around this axis. What am I going to get? True. What's it going to look like, though? It's going to be like whatever's over here is kind of just going around it, right? Okay? So our goal is to figure out the volume of that object. So I think I explained this a little bit yesterday, maybe not. But why do we do this? Because if I take a line, and we'll do an example in a minute. If I take a line and I revolve it around the x-axis, what kind of three-dimensional shape do I get? I'm going to end up with a cone. So this will be like its image over here. And we get a cone, right? Now, what's the volume of a cone from geometry?
1/3 pi r
Pi r squared times height, right? Okay. That's the volume of a cone. Did your teacher ever prove why it was 1/3 pi r squared h?
No, I don't
No.
understand any of those.
So when we get into the disk method, we can prove why the volume of a cone is actually this. Or, how about this one? If I take a circle or a half circle and I revolve it around the x-axis, what do I get?
Sphere.
I get your sphere, right?
Yeah, but we're not.
And so what's the volume of a sphere?
4 times pi r squared.
4/3 pi r cubed. So we can prove this by using the disk method, okay? So this is one purpose of it. All right? All right, let's see where we go from here. Let's take a look at an example. So let's say we've got 2 plus x cosine of x, and we're looking at the domain between -2 and 2. Go ahead and graph it in your calculator just so you have something to work with. Okay. You should get something like this. What's ST? Nobody knows what ST is? Such that?
It's
Such that? That's your future, right?
I'm literally no one teacher. Unless you want to drop out of all your classes, you might get close to me.
All right. So we have this curve, 2 plus x cosine of x, and we're going to revolve this curve around the x-axis. What kind of shape is that going to look like? Can you visualize it? An hourglass, kind of? Yeah, okay, so first thing, just for your own sake, you've got this curve, and I'm revolving it around the x-axis, so basically to redraw it down here, you're going to draw the mirror image, right? The reflection of it. So something like this. And then you have circles. Well, I guess that's probably better like that. So you get some sort of base shape, right? Can you visualize that? Can you see that? Okay. So there's my better drawing of that. So our goal is to figure out the volume of this object. Now, from yesterday, we should already know how to do this. Because what's the general equation? The integral of the area dx. How do we know what the area is going to be? What kind of shape do I get? I get circular cross sections, so I just need the area of the circle, and therefore I need to figure out what. What's important about that equation? The radius. Okay. Well, yes, but what function represents the radius? F of x. Because we're talking about the distance from the x-axis, which is our center of rotation, up to the curve. This is the radius at this point. So, what's that? We use f of x as a whole because what are we doing? We're finding basically the slice of the cylinder, and so we'll use the f of x here for that radius. Then we're going to find the volume at this radius, and then we're going to add them all up. Okay? So it'll be the integral. Okay? Let's see. Just as a reminder, how do you find the area under the curve, though? If I just wanted the area under the curve. You would take the integral of, depends what I'm asking for, right? Okay. I would take I just want the integral, or I just want the area bounded by the curve and the x-axis. The integral of f of x from -2 to 2, right? But by definition, or by understanding it, it's taking little slices of rectangles and then adding them up, right? Okay. So let me write that down. So f of x dx, the integral from -2 to 2 in this case, we're saying that f of x is the what? What does f of x represent in the graph? It represents, yeah, but just finding the area though. It represents what? The length of the rectangles, right? And the dx represented the width, okay? But I'm not slicing this into rectangles anymore. I'm slicing it into what? Kind of, but actually cylinders. I'm cutting it into thin slices of cylinders, right? So instead of saying this is the height, what we need here is, remember the area formula, right? Okay? And then this represents the thickness or the height of the cylinder. Okay? What do I got here? So to determine the volume, instead of slicing it into rectangles, we're just slicing it into infinitely many cylinders. And so, Celeste, you were saying, but f of x changes along the way, right? Well, when we're talking about rectangles, f of x, the height changes along the way, right? So this equation deals with that. Okay? All right, going on. How do you know it's a circle? Okay, fair enough. How do you know the cross sections are actually going to be circles? Because what was the key word of this problem? We're revolving. And so when I revolve, I always get circles. Yeah, it'd be circles. Nobody knows. Just you. She doesn't know. Because we're finding, to find the volume, it's like stacking pancakes. You find the volume of each pancake and you add it up, right? You can't find the volume by finding just the area. You have to find the volume by finding the volumes. And so what is the three-dimensional shape there? So we had rectangles, right? Before to find the area. Now imagine taking that rectangle and revolving it around. What is it making? That's the cylinder.
Shouldn't make pancakes to demonstrate it in real life.
I should have, but no. All right. So let's take a look at this. This is often what an AP question will look like on these types of problems. This is a main AP question. Finding the area under the curve, finding the volume after a revolution. I can almost guarantee you it's going to be on there. Okay? Figure that out. You guys should be able to do that easy enough. Find the area bounded by f of x, the x-axis, and negative 2, 2. That should be a breeze. You should be done. Undefined variables. So, what do we got here? Remember, it's not x cosine of x. That's a word. The calculator's trying to read that.
Oh, okay.
You have to do what? X times cosine of x. If you just put the times button there. Okay. What's the equation for the area? The integral from negative 2 to 2 of f of x, right? Okay. So we're looking for the area of that, and after you plug that in, you get 8. Okay. Now part B is the lesson. Okay. Part B is what we're talking about today. Okay. What is the volume after we revolve it around the x-axis? So in the previous frame, you already saw the picture of it. So the equation, or the picture looks like this, three-dimensionally. So what's the general form here? What's the general equation? The volume is equal to what? The integral of the area, dx, right? So area is the integrand. And what's the limits? Negative 2 to 2, okay? Now, the cross sections are what? What kind of shapes? The cross section, though. Because when I say area is a two-dimensional. We get circles, right? What's the area of a circle? Okay, so the area of the circle is pi r squared. The problem is we need to identify what the radius is. Well, you have a disagreement here. Remember, earlier on, I showed you the picture. What kind of shape were we talking about here? Earlier. The semicircle. Now watch this. If I have cross sections that were bounded by, let's say this, and I have semicircles coming out of it that are perpendicular to the x-axis, it looks like this. What did this length represent in the semicircle? The diameter, because the diameter is the distance across here. So this was f of x, right? In this case, f of x was the diameter. What does f of x represent in this case? It's the radius. You get what I'm saying there? In this case, the distance from the center of rotation, the x-axis, to the function, that is the radius of each circle. Are we okay with that? Okay. So then I can replace r with f of x. The radius is f of x. So what's my area function going to say? No, just the area formula. Pi times f of x squared. So now that I know that that is my area equation, I can plug it into my integral. What's the equation for the integral then? Okay. So volume equals the integral from -2 to 2 of pi times f of x squared, and I just put in what f of x was. So you guys go ahead and figure that out. Say that again. What is radius? It means the distance from the center to the end, right? So if I'm revolving this, the distance from the center to the end, this distance is your radius, right? Well, how tall is this? It's as tall as whatever the function is. All right. What'd you get? 52? Is that what you said?
Yes.
2.429. Okay, cool. Are we good with this then?
Yes, are you good with this?
I'm good. Yes.
Okay. I wouldn't want you to not be.
I would hope that I understand this. If I don't, then
Me as well.
time to find another teacher, right? So in general, now we have a line here. If I rotate this about the x-axis, what kind of shape am I going to get? What kind of solid? A cone with the top cut off of it, right? Can you see it? What's the general equation for this?
Circle.
The general equation for this.
Oh, the general.
Yes, but in this case, in all these cases, whenever you hear revolve, what is the cross section? Cross section circles. We're talking about cylinders. So therefore, the area is going to be the pi r squared, right? And in all these cases, at least for now, when we're talking about the x-axis being the center of rotation, what represents the radius? F of x. So our general equation, and my internet just decided to stop working.
Well, time to put the iPad.
Oh, wait, not mine.
All right. Well, we'll wait till that decides to go good. All right. So the general equation, write this down next to that if you didn't already. It's the integral from what to what? A to B of. Remember, it's the area, right? So what's the area? Pi. What's the radius?
F of x.
F of x.
Squared.
And that'll be squared, and then dx. You guys okay with that?
Yes.
Let's see if this is working now.
Sure. It's because, okay. Go ahead. Tell me.
Okay. So now, remember, in terms of integrals, what can you do to simplify this if you want? What's one thing you could do? The pi is a constant, right? So I can just take it out. So this is equivalent to pi times the integral from a to b of f of x squared dx. Does that really do anything for us? Not really, but this is how most of the AP readers look at things. Not that it matters, but hey. Mm-hmm. All right. Okay. Shh. So f of x is the radius, like we said, and therefore pi times f of x squared would be the area of the cross section, and that's why it's the integral of the area dx. Okay? So that's the general equation if you're revolving about the x-axis. What if you're revolving about the y-axis? It's easy. Everything has to be in terms of y. The limits have to be y's. You have to rewrite the equation in terms of y's, but the equations are exactly the same. Okay? Let's take a look at an example.
No, don't change it yet. Well, I'm not having you bring the square down.
Good now?
No.
How about now?
Okay. Yeah.
All right, you guys give this a try. Time to get out of here. 1:30? Okay, what is the volume of the solid generated by revolving? So what are you thinking? Disk, right? Circles, cylinders. Revolving f of x about the x-axis. What kind of shape do I have? Parabola. So can you visualize taking a parabola and revolving around the x-axis? That's the graph, right? Now obviously the parabola keeps going, right? But we are looking for the volume of the solid that's generated. This function is going to keep going. And so if it keeps going, then when I revolve this, this stuff's going to revolve over here, right? Is there going to be any bounds to it? So there's no solid over there. So the solid is just, how are you going to find the bounds? Find the zeros. Find out where this function intersects the x-axis. Okay? So do that. Get this in your y list. Find the zeros. What are your zeros? 1 point, what is it? Okay. So finding the intersections is going to be, you said 1.585 something?
Yeah.
And 4.4. Why did I write all those numbers down?
Because you're crazy.
Yeah, I'm crazy, sure. There's a reason. Okay, the bounds, these are bounds, right? Is this the final answer? No, so if you're going to round and then you're going to plug those into the limits and then find, your answer is going to be off. It's going to be off by, let's say the answer was 2.752 and you get 2.754. They're going to mark off a point. I know. So you've got to write it all out and use all the numbers for your limits, for your bounds. Okay? So again, the volume is equal to the integral from the lower bound to the upper bound of the pi times radius squared. So what's the radius again? The radius in this case is f of x, so I just wrote that down there. Anybody have an answer yet? What did you say, Trav? 18.956. Very good. Are we okay with that? Okay. I have to go on. We have 2 minutes and I have to go on.
No, you don't.
All right. So, like I said before, what if you have to revolve it around the y-axis? Okay. Well, let's look at an example. It's going to be the same exact process. You just get everything in terms of y. Okay. Same exact process. So let's see here. Let's look at the example. Come on. If I got just y equals x squared, and it's bounded by y equals 4.
How do you find the new limits again for if you convert it to y?
You'll see. Oops. Okay, so you see that right there? I'm taking the parabola and I'm revolving it around the y-axis, yeah? Okay, so it's going to look something like this. So the other side of the parabola is not just the other side of the parabola, it's the reflection, so it's the revolution of it, right? Now, if we're talking about the volume, what is the limits? The limits are no longer going to be this way, the limits are going to be this way. So what's the lower bound? 0. What's the upper bound? 4 in this case. There's how you find it. I mean, there's other things you have to see on other examples, but that's it. Now, what represents the radius? The radius is represented by the distance from the y-axis to there. So that's why we have to get the function in terms of y, and whatever that is, that will indicate what our radius is. So x equals what? X equals rad y. So what's my equation? The integral from 0 to 4 of pi times rad y squared dy. And that simplifies to what? Just the integrand will be then y. And then you could do this analytically without a calculator by taking the antiderivative, plugging in, and getting your